Okay, hello and welcome to our talk When Good Turns Evil, using Intel SGX to stealthily steal bitcoins. Great that so many of you showed up, so I hope this is an interesting talk for a lot of you. Let's talk shortly about the outline of this talk today. You all know bitcoins, and then you have these wallets there that you need to store your bitcoins, and then you have your private key in your bitcoin wallet that you have to protect at all costs, so no one should have your private key that you use for your bitcoin wallet. Otherwise, anybody could use your private key to make transactions with your money, literally stealing your money, which would be really bad. So you really want to protect your bitcoin wallet. And then you have this nice hardware feature by Intel, it's called Intel SGX, that allows you to run applications in a secure enclave and hardware, so it's hardware supported isolation. It allows you to run programs, store data, and make it completely secure so that no one can get access to your code, to your data. Everything is encrypted. It's enforced by the CPU. So what's better than using that, combining that with your Bitcoin wallet? So implementing your Bitcoin wallet inside Intel SGX, this secure enclave, which protects your private key by encrypting the memory, by not allowing any other application or operating system to access the data, to access your private key. So that sounds like something we might want to do, right?
True. So we have this nice technology, but as an attacker, why not use this technology as well? We can also use SGX to hide ourselves from the operating systems, any antivirus software, because no one can look what we are doing. And maybe as an attacker, we can also attack other enclaves running inside SGX. If we can do so, we can steal the bitcoins and you're doomed again.
Okay, so that was the outline. To our persons, my name is Schwarz. I'm a PhD student at Graz University of Technology in Austria. I'm working on side channel attacks, on microarchitectural attacks. So all the attacks that exploit some side effects, we only do that in software. So we work on software-based side channel attacks to exfiltrate secrets anywhere, typically using the cache or the branch predictor or the DRAM. You can reach me on Twitter. It's my Twitter handle there. You can write me an email if you have questions, if you want to get in contact. We will also be here for the rest of the conference, so you can just come to us and talk to us if you're interested in that stuff.
And my name is Moritz Lipp. I'm also a PhD student at Graz University of Technology. I also focus on side channel attacks. You can also contact me on Twitter or via email, or just talk to us later on. But we were not the only one working on those subjects. So our research team consists of Daniel Cruz, Clementine Maries, Samuel Weiser, Thomas Schuster and Stefan Mangard, also from Graz University of Technology, and Anders Fogg, who is working at G-Data Advanced Analytics. So let's dive back into our topic. How does SGX work?
Exactly. So we have seen there is some hardware support for running things securely. So, but how does that actually work? So I guess not all of you have heard about SGX and how that really works. So I'll give a brief introduction to SGX. And if we're talking about applications, we usually have one application with the secrets in there and all the code. And with the SGX model, we split our application. So we split it into an untrusted part, where we don't have any secrets or anything critically stored. And this untrusted part is responsible to create this enclave. And this enclave is the trusted part of our application then, containing all the secrets, all the code that should not be attackable. And everything is stored in there. It's encrypted in a DRAM. And if we want to call any function inside the secure enclave, we have to go through a call gate. It's similar to how untrusted applications interact with an operating system. They use syscalls there. Here we have a call gate with O calls and E calls, and we call into this call gate and it gets dispatched to the correct trusted function we want to call. This trusted function does all the computation with the secrets in there, and then if it's done, returns, and in the untrusted part we just get the result of this operation, which was done in the trusted part. And then we can continue our whole computation in the untrusted part with the secretly computed secret of the trusted part. And the nice thing about that is that it gives us quite some protection, even in a way that we can assume, the SGX trust model assumes that the operating system is compromised. So the operating system is evil, we have a virus for example, and tries to get the secrets out of the enclave. And we can't do that, so there's no access from the operating system to the enclave. We are protected against certain hardware attacks, such as sniffing on a DRAM bus, or doing a cold boot attack, because the DRAM is encrypted, and we can't see anything that's going on in there. In fact, the operating system sees everything that's executed in there just as one single function call, cannot intercept anything there, doesn't see anything. So quite a good protection. That's why people decided, okay, let's use that feature of our Intel CPU to implement Bitcoin wallets in there. For example, there's this Ledger SGX enclave for blockchain applications. We have a BitBay Kobe Bitcoin wallet that's implemented in Intel SGX. There's even a payment channel called T-Chain that's using SGX as a trusted third party. And we took one of the snippets out of the paper there, and the T-Chain paper, the authors assume that the trusted execution environment guarantees to hold and do not consider that they all hold and they do not consider side channels. So side channel attacks are out of scope for their trust model. And we might see that this is not something you want to have, that you consider side channels out of scope. Okay, but we need something for blockchain bitcoins, right?
Yes, so before we see that side channels are not a good idea to make them out of scope, we need to think, what are we going to put into our SGX enclave? So of course we are going to put the crypto there because we have our private key which we want to protect. And what we want to do, we want to sign our transactions so that no one else can take our money and just spend it. That's why we have those signatures, for instance like an RSA signature. And it works as following. We have a simple exponentiation with our private key which we want to protect, and if you want to implement that, you use square and multiply, for instance. And the nice thing is that when the key bit is 1, you use square and multiply, and if it's a 0, you just use square. So the implementation is quite forward. And you do this for every bit in your key. And as you can see, the multiply operation corresponds with the 1 in the key. And if by any chance you can possibly monitor whenever the multiply operation is called, you can directly infer when a 1 bit has been set in the key. And therefore, you can find out what the key is. So you do this for every bit. But with Bitcoins, we use elliptic curves. So we use ECDSA to sign our transactions. And it's quite similar, but we use point multiplication instead of the RSA exponentiation. And when we want to implement that, we use double and add instead of square and multiply, or the constant time Montgomery ladder, which is nice because it protects us against timing side channels and also Bauer side channels. But what you have to keep in mind that both algorithms use secret dependent memory accesses. So they access some memory locations dependent on the key. And why this is important, we see in a second. Because for instance, we have so-called cache attacks like the prime and probe attack. And cache attacks exploit timing differences depending on whether data has been loaded into the cache, so the timing access to this data is fast, or we have a cache miss where the data has not been in the cache, so we have to load it from the memory, and the timing access is slow. So prime and probe can be used to monitor memory accesses. And this corresponds to what we want if we want to attack like the signature creation, where we have those secret dependent memory accesses. So maybe we can use prime and probe to find out the key. And what is important, that the prime and probe attack only attacks a part of the CPU cache, namely a cache set, which we'll see in a second where we illustrate how the attack is working. What's nice about the attack that it also works across CPU cores. So we do not care if one application is running on the first core and the target application is running on the other core, because we can still apply the attack, because on Intel the last level cache is shared among all cores. So how does prime and probe work? On the left you see the address space of the attacker, on the right of the victim, and in the middle you see the cache. So the first step, what the attacker is doing, it just loads addresses that he owns into the cache, filling up one entire cache set. So every data that is in the cache set belongs to the attacker. Now the attacker schedules the victim. The victim maybe decides on, depending what he is doing, to load an address that maps to the same cache set, and therefore loading the data into the cache and evicting data out of the cache that belonged to the attacker. And in that case, this happens 2 times. So the cache set is not filled anymore with data belonging to the attacker, but also data belonging to the victim. What the attacker now can do, he can probe if his own data is still in the cache by just measuring how long it takes to access those addresses. And as we can see, the first block is still in the cache, so the address loading is very fast. But for the second block, it has been evicted by the victim, so the memory access is slow. And therefore, we have a timing difference where we can deduce if something has been accessed and loaded into the cache by the victim. So we can combine this to attack. How does this work?
Okay, so we have this algorithm with secret dependent memory accesses, and then we have an attack that detects memory accesses. So we want to combine that somehow. We have our victim that, as said before, uses SGX to protect the private key and all the signature. We of course need some API to interact with this secure enclave. So our wallet API there. And on the other side, we have the attacker. And the attacker wants to also leverage Intel SGX to stay stealthy, because it's also the attacker can use SGX to get protection from anything else, so that no antivirus can detect or stop it. That's why we want to implement our key extractor within the SGX enclave and just have a benign loader that does nothing else than create the enclave and call the attack function, which is inside the SGX enclave. So on the hardware side, they can run on different cores. We don't care about that. They have their own L1, L2 cache, but they have their shared last level cache, which makes it perfectly applicable to mount a prime and probe attack there, because we have this shared cache and we can mount at what you told us.
You really want to mount a prime and probe attack in SGX?
Yes.
That's not that easy.
Huh.
Not at all. Because first you want to measure if something has been loaded into the cache or not. So you need a really high precision timer, like RDDSC. But inside SGX you don't have that timer, so you cannot measure with a high precision. In addition, you do not have any syscalls that you could use, for instance, for the perf event interface on Linux, where you could also get a high precision timer. You don't have syscalls at all. How do you want to do that? Also, you do not have any shared memory. You do not have any information about physical addresses that you need to build up the eviction set, because it's not that straightforward to just fill the cache. You also do not have any large pages that you could use to get some information about the physical addresses. You have nothing of that.
Oh, okay, let's start simple. Okay, if I don't have access to the high precision timer, I'll just build my own timer.
How do you want to build a timer?
Oh, I mean,
the timing resolution must be in the order of cycles, so very, very precise. How do you want to do that?
I mean, that's simple. You learn programming, right? I just start a thread, and this thread continuously increments a global variable, and that does it all the time, does nothing else. And then I can use this global variable as my timestamp, because I don't need any wall clock. For me, it's sufficient to measure timing differences, so it's totally fine if this does not correspond to any seconds or something. I just need something that counts monotonically.
Okay, and this should work. Let me try that out. So for RDDSC, we have one increment per cycle, which is very nice. So I implement your idea with a loop, and actually that's not that bad. It's roughly 5 cycles that it takes to increment once. So maybe we can already use that,
Yeah,
but it's not even close to RDTSC.
But I know assembly. I can do it better than my compiler. See, it's a lot better.
Yeah, that's not much better.
Okay, I get it. But I have a really cool idea. Instead of incrementing this memory location, which has to fetch it from the memory, then increment it, put it back to the memory, I do something else. I use a register, increment the register all the time, and then just move the register only to the memory, so that I don't have to read from the memory.
And this should be faster?
Look at that.
Whoa.
It's even more precise than the hardware provided timer by Intel. So it's really cool. We have solved that problem, right?
Yeah, apparently. So you can use that.
We have a timer.
But that's only one out of many problems that you have to solve. Because, as I said, the cache set is determined by some bits of the physical address, and you have no information about that. So, without any knowledge, you cannot build an eviction set, regardless if you have a timer or not.
That's a good point, actually. But I remember something. There was this DRAM side channel attack by Pestle et al. In 2016. And they reverse engineered how memory actually maps to the physically DRAM, the DIMM in there. And what they found is that we have timing differences depending on where exactly the memory is in the DRAM. And now we have a timer. Because if you look at the DRAM in detail, it's divided into borders. And every time we get a row border, we know exactly, that's aligned with our pages, that the 18 least significant bits are 0. So that's of the physical address. So we get at least parts of the physical address, which are sufficient because we only need 16 bits of the physical address.
Can you show that in more detail?
If we can find the row border, that's fine. And if we now look at a physical page, a 4 kilobyte page, that's really divided into different rows in the DRAM. So we have the rows on the right side. They're in different banks and groups and channels. And that's really divided into, so every part of a 4 kilobyte page maps to different rows in the DRAM. And that depends on how much DRAM you have and on the microarchitecture of the CPU, but we know it for most of them. So we can do a nice trick. We choose 2 addresses, and we choose it with a certain distance so that they both fall in different rows of the DRAM. We know the row size, so that's not too hard. And we choose a distance so that we go into a different row in the same bank of the DRAM, that we always have that case if a new row starts. So directly at the row border, we get such a conflict there, and then we know from a high timing that we are at the beginning of a new row, and with that we know 18 bits of the physical address. And we can just iterate over our memory there, measure the timing with our now good timer, and get timing differences and high timings when we are at the row border. And I tried that, and you can see it actually works. So we have these timing peaks here where a new row starts, and at this address I know the physical address.
Impressive. So now to sum it up, you used your counting primitive to measure the DRAM accesses. Then through the DRAM side channels you determined the row borders. With the knowledge that for row borders the least significant 18 bits are set to 0, you know that they map to the cache set 0. So you can use that to build the eviction set for the prime and probe attack that we explained earlier. And then you can just mount the prime and probe attack on the buffer containing the multiplier, monitoring whenever a key bit is set to 1, otherwise to 0, and therefore you can get the private key.
Exactly. See? Really easy.
Yeah, sounds nice in theory, but does this really work?
Let's look at the results. So we actually did that for a 4096-bit RSA private key with an embed TLS running in an enclave and attacking that from a different enclave. And see, there's the key.
Yeah.
Easy to see, right?
I see noise and
okay.
dots. Where's the key?
Maybe we should add some simple pre-processing. Simple moving average over that gives us already some spikes there. And if we look closely at them, they really correspond to the key bits of the private key. So we can see a spike there corresponds to a 1. And if we don't have a spike, then it's a 0. The zeros are faster to calculate because we don't have so many operations, so they are not, so they are a bit smaller than the ones, but that's just simple matching the ones and the zeros in there. So we can actually extract the private key from the enclave.
You're using the prime and probe attack, right?
Yes.
So you have many cache hits, many cache misses. We have performance counter, so we can just monitor whenever you mount the attack. And it's easily detectable.
Yeah, that's if you mount the prime and probe attack. But when I do that in the SGX enclave,
okay,
then I have this additional protection where the SGX enclave protects me as an attacker and does not allow anyone to see the performance counters. So if I look at the performance counters showing me the cache hits and misses, and I do that inside SGX, I can't see anything. And the small bars here are just the noise outside the enclave by calling the functions there and the loader application, the API. So perfectly hidden.
Sounds bad. Can we do anything against that?
Of course. So we can of course fix that on a source level. We have this cache attack that attack our code, and if we can change the code, then we can also fix stuff there. So what we should do, what we should have done for years now, sad thing is, doesn't happen that often, is that we have to use side channel resistant crypto implementations. So we have such implementations. We can do things for RSA, for example, with exponent blinding. We have bit sliced implementations that do not have secret banded memory accesses anymore, and then I have no chance of attacking your crypto implementation inside the SGX enclave. So we really should use that. We could of course do something on the operating system level.
But before that you said that we do not trust the operating system.
That's of course right. So that would weaken our threat model because SGX assumes that we do not trust the operating system. Still, we could add some countermeasures to the operating system, like giving them an API to inspect the code or enable certain performance counters for last level cache hits and misses, so the operating system can at least detect that something is going on, not exactly what, but that something is odd. We can implement stuff like enclave coloring to prevent cross-enclave attack, which means every enclave that is started gets a different part of the cache with different cache sets, and if you don't have the same cache sets in the last level cache, then we simply cannot mount a prime and probe attack. So that prevents any attack cross-enclave, meaning I as an attacker cannot use SGX enclave to stealthily mount this prime and probe attack, and I can only do it from the outside, and then it's easier to detect. So we could do that. We could also add some randomization, as we do all the time everywhere, to make attacks harder, like a heap randomization. Then my multiplier would be all the time somewhere else. That doesn't solve anything, but it makes it harder for an attacker because it's not that predictable where he has to attack, and it makes attacks a lot harder. But sure, that weakens the trust model. So finally we should get rid of that in hardware. So we can't do that, Intel has to do that. Intel could add things to SGX. For example, there's already this cache allocation technology that participates the cache so that different applications cannot influence each other in the cache. And that could be combined with SGX so that if we enter an enclave, it automatically partitions the cache, and every enclave gets a different part, and no application can access this part of the last level cache because it's only for the enclave, and then the enclave is completely isolated in the cache and no one can mount a prime and probe attack on the cache. Right now that's only controllable by the operating system, but that could be combined with SGX in hardware. We could also have some form of secure memory element, like providing a small memory element that's not shared, that's never cacheable, just for certain operations inside the enclave, like signing operations, encryption operations, so that it's not shared with the insecure world, and then we cannot attack that because we don't have access to that. That must be of course also mutually exclusive to one enclave, otherwise we again get these cross-enclave attacks. So that are some of the things we could do to prevent such attacks to not lose our Bitcoin private key.
True, so you cannot steal my Bitcoins anymore. But we have another nice attack that we want to show you, where we exploit non-side-channel bugs, but we utilize side-channel attacks to actually exploit them. So imagine a scenario where we now have side-channel resistant crypto, so you cannot attack it anymore, you cannot steal my Bitcoins anymore, which is nice for me, because they are mine. And we put everything inside the enclave. And as you said, we do not have any source code. The binary is encrypted from the enclave, so we cannot inspect it from the outside. So it's basically a black box that has an API that we can talk to. And that's it. And for instance, what you could do in that scenario would be a simple DRM video player. Because if you buy a video, you should only be able to watch it like once or twice or in a certain time period, because otherwise you have to pay another time, so I can earn more money if you want to watch my video. Which is a classical digital rights management scenario, where SGX is also useful to implement things like that. So we have an encrypted video file with a signed header, so you cannot tamper the file. The header contains a validity period, which states when you are allowed to watch the file. So you can only watch it for 1 week, for instance, after you bought it. And the video player checks whether the current time is within this period, otherwise it would not allow you to play it, and also if the signature is valid, because if you have modified the file, it would also not play the video. So we have a nice, secure DRM video player. It will play the file even using Intel's protected audio and video path, so you cannot just record the video and then watch it again because you just use the screen recorder. You cannot use that because of that technology.
Yeah, but I really do not like DRM. So, yeah, now I stole your Bitcoins that you thought you protected, and I want to keep my stolen Bitcoin. So I don't want to pay for the same movie over and over if I want to watch it again. So I really don't like your DRM player and scheme. So I want to break that.
Yeah, okay. So this time it won't be a cash attack on crypto.
Yes, so, it's resistant crypto in there.
Yeah. So let's take a look at our code. We have a simple function which gets the DRM file as a parameter, which is our protected video. And then the first thing that we do, we check the signature. So whenever you tamper with the file, we detect that, we return, and you are not able to watch the video, because this is what we want. The second check that we do is we check if the file has expired in the meantime. So we get a secure timestamp, and when it's 1 week after you bought it, you are not allowed to watch it anymore. So we have a second sanity check which is working, and we detect that. And in the end, if everything is fine, if you bought for it, if you haven't tampered the video file, you can actually watch it. So this is what we wanted to do in the first place. But although the code looks correct, right?
No, I haven't seen any bug in there, so that.
But there's like still a problem in there. Because SGX enclaves can access non-enclave memory, because this is convenient. And therefore memory is often shared between the enclave and the loader. And this can create race conditions. Do you have any idea why this could be a problem?
Oh, now I see. There's a problem with our code, because now we also have multi-threading, right? We can run things in parallel. So if we go back at the code, I see we have this DRM file, which is then a shared memory object, because we don't want to copy everything in there. We just provide the pointer, as we see, and there's a shared memory object, and then we access the shared memory to check the signature, and afterwards we access again to check whether it's still valid. But in the meantime, I could in parallel change the headers and make it valid. So the signature check was okay, and then I changed the headers, and then the signature is never checked again, and the validity period, yeah, is then fetched afterwards. We have a time of check to time of use bug. We check something before then and we use it afterwards, and we expect it not to change in the meantime. So after the signature check, we can do anything with the header that we want to do. And this allows us to set an arbitrary validity period, because we can just change that in the header, which is only signed. And because we access the memory twice, we fetch something twice from the memory, we also call those bugs double fetch bugs, because we fetch it twice the same data from the memory. But we cheated, right? I mean, if we have the code, it's really easy to see. If we know this kind of bug, then we can see that. So that's really cheating, because you said we don't have the code, we don't have the binary, so we cannot analyze it for such bugs. So that's still like security by obscurity, right? It's kind of fine.
I get what you're saying, but you're not entirely correct. Because as we've seen, memory accesses are visible in the cache. So also if you run your code, it will access memory, of course, and those accesses can be visible in the cache. So what we can do, we can again use a cache attack to observe those memory accesses and therefore detect if a double fetch bug has occurred or not. And this time we even have shared memory, which makes everything easier. So we do not have to use the prime and probe attack, where we have to build our eviction set and have to have so much knowledge. We can make use of the shared memory. And what we can do is the so-called flush and reload attack. So we constantly flush the address that you are changing from the cache using the clflush instruction, which is an unprivileged x86 instruction, which just removes one address from the cache. So it won't be in the cache the next time someone accesses it. Then we just schedule the victim. The victim may access the address, loading the data back into the cache, or just do not access the data. Then it won't be in the cache. And the next time we measure the access time, we can indeed distinguish if the data has been loaded to the cache or not, and therefore if the victim also has accessed the data. So if the access is fast, the victim has accessed the data, we can see this in our trace, and we know if it has been accessed a second time that we have a double fetch bug. So if we look at a simple plot from such an experiment, it's easily visible the point of time where the victim process has accessed the data. In the scenario of our video player, where the data has been accessed twice, we can also see that in the trace. So we have those two distinct spikes telling us that the video player has accessed the data twice and that this might be a problem. So we see the first access and the second access. So cache attacks also allows us to dynamically detect double fetch bugs in black boxes. So for instance in an SGX enclave or in a trust zone trustlet, where we do not have the code, where the binary is encrypted, and where we just can use this solution to detect a double fetch bug.
So how reliable is that?
Yeah, the thing is, the further apart those memory accesses are, the higher the probability, of course, because our attack code also needs to execute some instructions. And the minimum time that we've measured is around 600 cycles that those memory accesses need to be apart so that we can detect that using the flush and reload sidechain.
So I'm not good in cycles as a unit, so can you give me an estimate? How long is 600 cycles?
It's only a few memory accesses, so that's not a lot.
Okay, so one memory access is like 200 cycles. So
exactly, so about 3 memory accesses. And if the time between those accesses is more than 3000 cycles, which is also not a lot, if we have seen the code where it does some computation, we have a detection rate that is very close to 100%. So we can say for sure if there has been a double fetch or not. And using this, we have an automatic solution to detect these double fetch bugs in many scenarios.
Okay, so that means we have this nice, we can again use a side channel, we can again use the cache, it's a powerful microarchitectural element to detect double fetches in any black box anywhere. We don't have access to the code or to the binary, which is nice. But I'm more the kind of guy that tries to destroy things than to make them more secure. So I like the detecting stuff, but I also want to exploit it. Can we exploit that? I mean, I want to exploit that.
Not that easy. I mean, you need to change the value in this small time window that we have. Otherwise, you cannot exploit it, which would break my video player. And when we take a look at state-of-the-art exploitation, what they do is they just flip the value constantly, all the time, and hope that they hit the time frame so that they can really exploit that. And this has a very, very low probability. So the chances that you can exploit it are not very high.
But I have an idea. We just need a trigger. We just need some way to detect when the first access was as a trigger, right?
Yeah, this could help.
And you said detection is easy because we can see it in the cache. So why not use the cache side channel as a trigger? Because we can already detect all the memory accesses in the cache. And if we know when the first access was, then we also know when we have to change our values, right? We detect the first access. We do not even care about the second access. So it's even better than a detection. We really don't care how far the two accesses are apart. We only need to detect the first one. And if we see the first one, we simply change the value afterwards to the value we want to have. Because after the first access, we know the sanity check is done. And we can change our value to something we want to have in there. And if we look at that in the trace, so we see the detection and we have the first access, and then we have this time window until the second access, but we perfectly get a trigger signal on the first access. So we just modify the value in there, gives us enough time to do that and set it to any value we want to have, any validity period. And then on the second access of your DRM player, it already works with the wrong value, the value I have provided. So
this again sounds very nice in theory. I actually brought the video player with me. So can you really exploit that?
I hope so. So let's look at that. Oh. Well, so I have the video player code in here, and I already prepared the attack code because I don't have that much time here, and I just comment that in. And what we see here is that we have this enclave call to play the file, and we want to attack this header field, this valid2, and we just want to set it to a different valid2 period afterwards.
So first you maybe need to show.
Yep, let me show.
If the player is working as expected when you're not running the attack.
Yes, first let me show that the player does something. I just have a... So, let's first start the player with something. Okay. Start the player with some demo video. And it says, okay, I can watch this until 2020.
So you bought it?
I bought it, yeah. And oh no, it's on the wrong screen. And I can actually see some video playing. Okay, that's fine. So the player is actually working. And then I have one video I bought that I wanted to watch. It's a movie. And oh no, the file has expired.
Wow.
So I didn't pay for it. Okay, but I still want to watch it. So I comment in my attack code. So until when should we make it playable? Any favorite year in the audience that's in the future?
You can say anything? 3000. Okay.
3000. I hope the C library accepts that in the future. Okay, then it should be valid until the year 3000. Then what we simply do, I start my attack function that creates another thread, does the multi-threading part. In this thread I have the flush and reload that acts as the trigger, and if it finds the first access, then it changes the value to the one that we want to have. So let's rebuild the player. We don't change anything in the enclave, we don't have access to enclave, just the functions outside. And then I want to play the movie.
So
and
it's been toggled?
It's on the wrong screen. Wrong screen.
You clicked on it.
And it says valid until January 3000. So we have a long time to watch this movie. And we can say play. And we can actually watch this movie. And we have defeated this DRM protection that you have implemented there.
Oh,
so
no.
this actually works really reliable with the double fetch detection and then exploitation here and we have this video running, which we should not be able to view. So, it does work, what we proposed. Perfect.
True. So, how can we prevent that? Because we do not want to end with my broken video player. So, double fetches itself are not bad, because sometimes they are necessary. Sometimes you need to code it in a way that you have double fetches. The only problem that you have is when you change the value, and this leads to an actually exploit where you can do something, like with the video player, where you then are allowed to watch the video even if you would have not been otherwise. So we have a problem there. And nowadays we even have frameworks that allow us to exploit such race conditions in a very, very good way. And with the cache trigger that we've just seen, they also get very reliable. So as we've seen in the demo, it worked right away. So,
but I have an idea how we could fix that.
Okay.
So the problem was, I mean, we have this time in between to change the value, but we can just ensure that both the fetches, so we leave double fetches in there, we just ensure that both accesses are atomic, so they appear as one.
I mean, you have so many instructions in between.
Yeah, I know that.
How can this be atomic?
Maybe that does not work on the CPU architectures we have right now, because, yeah, of course, we can only do that some certain things in parallel. We can't make them exactly at the same time, so they cannot be really atomic. But maybe it's enough if they look atomic. So from an attacker's perspective, so they're not atomic, of course not. So we have to fetch once, do something, fetch again. So that cannot be one operation. We just can't do that in our CPU architecture. But we want to make them look atomic, so that even though they are not atomic, the attacker thinks they are atomic, because the attacker cannot see any time window in between. The attacker only sees one operation.
Actually, the idea is very good. And as you maybe know, we have such mechanisms already in modern Intel CPUs. We have Intel TSX, which provides exactly this functionality, that accesses appear to be atomic in hardware. And the idea is that Intel TSX is an implementation of hardware transactional memory that you might know from databases. So we ensure that multiple reads and writes are atomic, and we just wrap all those operations that we want to be appearing atomic in one transaction. And if something conflicts, we just roll back to the previous state, so nothing has actually changed. We can detect that, and therefore, if no conflict has occurred, everything is fine, everything appeared atomic, and we're good. And by coincidence, this is implemented using the cache. So how does this work? We have the cache in the middle again. On the left, our thread 0, on the right, thread 1. And thread 0 uses xBegin to begin such a transaction. Then it will execute some instructions and end the transaction with xend. If this completes, everything is fine. Otherwise, the transaction will abort and we will go to the else path. So, thread 0 reads some data. Therefore, we have a read set, and also thread 1 reads the same data. No values have changed, so everything is still fine. The second step, thread 0 reads some other data, and thread 1 actually writes something. So we're going to update the read set. Within the read set, no values have been changed, everything is still fine. But now, in the third step, thread 1 writes something into the data within the read set, which thread 0 tries to read. So actually thread 1 modified the value, and therefore we abort the transaction. You might have noticed something now. Actually, what we see in this example is a typical double fetch bug, where we have the first access to the value, then the other thread modifies the value, and then we have the second access where we reuse that value. So exactly the bug that we've seen earlier. But this time, the transaction aborts, and therefore we can detect that and do not continue the rest of our application. So we still do not do that by playing the video, as we've detected your attack.
Okay, so we can now detect it, and that works really reliable because it's implemented in hardware, It's a hardware feature that we can use. And so we also created a small library with that called Dropit that prevents such exploitation of double fetch bugs using TSX. We also have it open source, so you can try it out. It's especially useful in an SGX scenario, so we only have small code bases where we want to actually protect them from any exploitation. So we can just wrap it with this library. It's really easy to use. In the easiest case, we only have 3 additional lines of code that are sufficient to protect any double fetch from being exploited. And we can apply that to our code. It doesn't only work for SGX code, we also did that in the Linux kernel. It also works there to protect everything. But let's look how easy it is to use that on our code. If we have this DRM player with the file, we just have some initialization. We say, okay, we're going to retry 10 times. So if it fails for some other reason, which might be the case because the cache is used a lot by other applications running at the same time, then we might want to retry. We don't have any false positives there. And then we just say start the protection and end the protection. Start it before the first fetch, end it after the second fetch, and everything in between is atomic for any outside attacker, any outside viewer. And if someone tries to exploit that, it will fail more than 10 times. And then we just go out there and say there's something fishy is going on. We don't want to continue here, and everything is safe. So that's really easy. It's just these 3 additional lines of code that we can add there to make an exploit impossible using this hardware protection. So it's really efficient and easy. If we have this, it's a complex problem. Double fetches are really hard to detect. They're really hard to fix because they're often necessary. And then we need complex workarounds, retry logic, and different logics to prevent double fetch exploitation. But if we have TSX, then we have a really easy solution for many double fetch scenarios to fix them or make them non-exploitable. It's also fast. It's implemented in hardware. It's better than any software lock workaround version. So if you use traditional locking, traditional TSX is approximately 18% faster than traditional locking. So even gives you better performance and better protection. Of course, one of the critics here is it's limited to CPUs, to Intel CPUs and to new Intel CPUs that have that feature, because not all of them have. But many CPUs that have the SGX extension also have the TSX extension, so we can secure most of our enclaves with the TSX feature, which is really cool and makes it easy to protect that bug from being exploited.
So in the beginning you stole my bitcoins, but we fixed that. Then you broke my video player, but we also fixed that. So what did we learn today?
What we learned, the main takeaways: side channels can cost you money. Does not matter whether I directly steal your bitcoins or if I do not pay you for watching the video, or for whatever reason. Side channels are something you should consider in your threat model. They are nowadays not that hard to mount. We have many side channels, so they can really cost you money because an attacker can use them.
So it's really important that you do not consider side channels out of scope, as we've also seen in the beginning of this year. Side channels are very applicable, even in the scenario of SGX, and very many other scenarios wherever you share resources, you might run into a problem with side channels. Therefore, do not consider them out of scope, and keep that in mind also if you use those technologies.
Exactly, and do not take hardware extensions as the silver bullet that you just can add to your code with all your bugs, with all this exploitable stuff in there. So if you have exploitable code with bugs in there, it doesn't matter whether it's a normal bug, as we've seen, memory corruptions or double fetches, use after freeze, whatever, something that's known for a while, or whether it's something that's only for exploitable with side channels, like non-side channel resistant crypto, or other secret-dependent memory accesses that can be exploited with side channels. If you have exploitable code and you put it in a secure enclave, doesn't matter whether it's Intel SGX, ARM Trust Zone, it's applicable to all of the hardware enclaves, then you do not get secure code with that, you only get exploitable enclaves. So then the code inside your enclave is exploitable, and that can be even worse because you rely on it to be secure, and then it's also a nice target for an attacker because the attacker knows exactly where your secrets are. So you should not have exploitable code just put into secure hardware elements, but you have to write secure codes so that you can use then in addition these hardware features to make it really secure. So that's one of the really important takeaways if you write software using such hardware features. Okay, and this concludes our presentation. So thanks for your attention, and we are open for any questions. Yes?
I have two quick questions. First one is that the TSX solution at the end is only prevent the exploit, right?
Yes.
It doesn't pass the side channel leakage.
Exactly. So the side channel leakage is still there. So for the first attack, if you mount a side channel attack, for example on crypto, that cannot be prevented with this library. But there is a paper from last year, Usenix Security, where a team of researchers found a solution to also use Intel TSX to prevent side channel leakage because it's implemented in the cache. So you can also see if someone does a cache attack with that and evict something from the cache, then that can be detected with Intel TSX because your read set is destroyed or your write set and it aborts. So the operation aborts before any leakage occurs. So you can also use it against cache attacks.
So the second part is the first attack on Bitcoin. How easy it is to launch from outside the enclave?
So from outside the enclave, it's a bit.
Or is it even possible to do?
Yes, from outside the enclave, it's even easier to do because you have all the features. You can get physical addresses because in this attack model you have root privileges. So you get physical addresses. You can easily build your eviction sets for prime and probe. You can also tamper with the scheduling of the enclaves. So you can, there's for example the SGX step framework that allows you to only let the enclave execute a few instructions, then interrupt it, then attack again the cache. So it basically slows down the enclave extremely, which makes it a lot easier to exploit these attacks from the outside. So if you are not in the enclave, it's a lot easier.
But you're also visible to the operating system. So you cannot hide within the enclave, as we've seen with the performance counter.
Yeah, there are detection mechanisms presented in 2015 or 16, Black Hat, that use the performance counter to detect ongoing cache attacks, and then you could stop them.
So if there are any more questions, but if you're still interested, you can check out the white paper, which has much more detailed information in there. Otherwise, you can talk to us later on, and thank you again.